Hello and welcome to today's lesson, least squares regression line for bivariate or two variable data. Okay, our objective for today, by the end of the lesson, I will be able to calculate and interpret the least squares regression line for two variable data. Okay, one thing we always want to look at is the why. Why is this an important skill for statistics? And what we need is we need the least squares regression line to represent the general pattern of the data to allow us to make predictions. The whole goal is using an overall data set to be able to make a prediction line so we can use X values as our input to predict the Y value for a specific situation. So now, when we look at our least squares regression line, okay, it can be written in two ways. The most common way for statistics is what we see here, y hat, because it's a prediction value, it's not an actual value, so we always have to designate that, equals a plus bx. Okay, now, probably not the most common way you're used to seeing the formula. You're used to probably seeing a line equation in y equals mx plus b form, okay, which is something that we can use, but in statistics, we use the form this way, a plus bx, because it more models what we're looking at overall. Okay, we want to think about it. What is that a value? The a value is our y-intercept. Okay, so it's the output value of y when x equals 0. And in most of our cases, that's the starting point of our data, is when x equals 0. So that's why we want to start with that value, shows us where the line begins. And then when we look at the slope of b, okay, b shows us how we are increasing or decreasing from that original value. So b can be positive or negative based on the association of the graph. So when we're looking at this, we should say y increases or decreases when the x increases by 1 unit. Okay, so it's your adjustment in y based on a 1 unit increase in x. Okay, so when we think about it conceptually, the least squares regression line gives us the line that best fits the data set. And we know it best fits, and it's kind of the title, least squares. Okay, it's going to minimize. So we're looking at minimizing the sum of the squares of the deviations from the line. And we'll see why we have to square, just like with a lot of our statistics. Squaring is something that we have to do to be able to get a specific value. So now we look at this simple 3 data point situation. Okay, and how is a least squares regression line calculated? The one point that's on every least squares regression line is the mean of x, mean of y coordinate value. So when we're looking at this situation, our x values are 0, 3, and 6. Okay, so we add that up to get 9, divide by 3. So we know, and we'll put this piece in, we know that the x value for this situation, x bar, is at 3. Okay, so we can put a line in there. When we look at our y values are 0, 2, and 10. So we add that up to get 12. 12 divided by 3 is 4, so 1, 2, 3, 4. Okay, and we know that we've got a coordinate point on our least squares regression line at that spot. Okay, now the next piece that comes into play for the least squares regression line is selecting a y-intercept. So what happens is, okay, we've got any of these y-intercepts that we can select. Okay, we know we wouldn't select anything above the point because we can see the general pattern of these 3 points is a positive association. So as x increases, y is increasing. So we wouldn't pick anything above that point. So now we have the choice of picking any y-intercept that's below the point, and our whole goal is just to minimize the distance between the point and the line. So I can pick a value here, create a line, and then we're looking at the distances. So we can see some of these distances here. A distance of 2. This is probably our biggest distance here, which goes from 4 all the way up to 10. Okay, so we've got a measurement of 6, a measurement of 2, and we have to understand these measurements, actual minus estimated, okay, can be positive or negative. So this one's a -2, +6. Okay, up here we're going to have a distance of about 3 or 4. And what we're trying to do is, since we have positives and negatives, okay, the perfect line is going to balance out. So we can see that this is almost balanced. -2, -3, +6. Okay, those are almost balanced overall. So we would just have to make a slight adjustment to this graph to help us get the proper line. So the proper line for this situation, and we'll put that in, has a y-intercept around +3, goes through the point, and then comes up here. So we've got a 3-unit distance and a 3-unit distance negative to go along with the 6-unit distance on the positive side. Okay, so if we tried to add up the 3, 6, and -3, 6, and -3, okay, we try to add all of those up, we're going to get 0 every time for these lines. Okay, so in that situation, what we have to do is square them. So we would square the 3, square the 6, square the 3. And we would get 36, 9, and 9, or 36 and 18, which gives us a sum of 54, okay, which is the minimal amount that we can have overall. If we looked at that other line, we know now that that other line, my prediction here was just a little bit off. Okay, this would have been a -4. So we've got 16, 4, and 36. Okay, so 16, 4, and 36 gives us a little bit more than 54. Okay, but when we use our red line, then we're getting the actual values that we're looking for distance-wise. Because we have a distance here of -3, distance here of -3, and then distance up there at +6 to keep that value balanced. So that's kind of the process of creating your own least squares regression line. Okay, but the good news is the calculator can do it for us, or we have formulas to be able to build the least squares regression line overall. Okay, so now we know, and we've worked off of, we've got our correlation value for our set of data, the same set that we've been looking at for the entire unit. We've got our x bar, y bar, standard deviation of x, standard deviation of y, and now we go to the formula sheet. The formula sheet gives us the equations that we need to be able to build the least squares regression line. So sometimes you're going to have to build it by hand based off of values, and other times you're going to be able to just use the graphing calculator to get the equation of that line. So now, if we're building it, first thing we have to do is start with what we call B1. Okay, they show you the form of the equation on the formula sheet. So B1 is our slope. So B sub 1 equals our correlation value, 0.72, times, and remember, this looks just like a slope, standard deviation of y, standard deviation of x. 8.8 divided by 13.7. Okay, so we do that calculation, we get our slope value of approximately 0.462. and we'll talk about that value and interpret it here in just a little bit. Okay, now we want to find our y-intercept. Okay, on the y-intercept, okay, the y-intercept value on your formula sheet is listed as b naught, or b sub 0. Okay, so we're going to plug in what we know into that formula. So b sub 0 equals y average, because remember, we know that the least squares regression line goes through the average of x, average of y. So we have y average minus our slope times the x average. Okay, and that will get us our y-intercept value of 43.17. Now, we've gone through, found those two values, and we can finally build our estimation equation. Okay, so y hat, estimated y values based on this data, equals our y-intercept, 43.17, plus our slope, 0.462, times x. Okay, now, that's if we have to calculate the least squares regression line by hand overall. Now, best case scenario, you're going to be able to use your graphing calculator. We always start in the same spot. Okay, we enter in our two lists of data. Okay, once we have those lists entered in, we go back into stat, calculate, and we did this in our correlation video when we were looking at trying to find the correlation. We want to do our linear regression. Remember, a plus bx. The other version works. You just have to be careful about slope and y-intercept. Enter. Okay, make sure that you have your correct lists selected. List 1, list 2. And then enter to get your least squares regression line. And you can see this line is a little bit different coming from the calculator than the actual equation we got based on the values, because those values were rounded values overall. So we can definitely see a slight difference. Y-intercept is a little bit larger, and our slope in this case is a little bit smaller, rounded to 4 decimal places, 0.460. Not much of a difference, okay, but you can see a small difference in that situation. Okay, so now let's start talking about this line equation and talk about the interpretations. Okay, so our line equation we had, y hat equals, and I'm going to use the one from the calculator, 43.34 plus 0.460x. So if we have this least squares regression equation, remember what the slope means. For each 1 unit increase in x, okay, there is an approximate increase-decrease of b and y. So for our situation, for every 1% increase in homework percentage, there is a 0.46 increase in the final test score. Okay, so that's how we would interpret this slope. Remember, it's always going to be a value that we want to put over 1 if you want to turn it into a regular slope. Now, if we want to interpret our y-intercept, y-intercept would be the final test score. Okay, that's my y coordinate variable name when x equals 0. So if a person got a 0 for their homework score, this prediction equation would predict that they would get a final grade of 43.34. Okay, remember, we have our correlation coefficient, our R value, which is direction and strength of the values. But now, what if we want to predict with our formula? Okay, so we're going to pull our formula again off of the calculator. And one thing that we always want to do, as soon as we get our equation, we're going to do some predictions with this equation based on scenarios. So now what we could ask is, what final grade could a student expect if they got 50% on their homework average? So if a student gets 50% on their homework average, what we're going to do is take our equation, and we're going to plug 50 in for x, and we're going to make this prediction. So we've got 43.34 plus 0.460 times 50 equals, okay, a 66.34 is what that student can predict to get if they only get 50% for their homework score. Okay, so remember, we've got this final score prediction here. Okay, we could do the exact same thing. You know, what if somebody does 75% on their homework? Okay, so we can go back into the equation and then just make the adjustment. If someone gets 75 on their homework, they can expect to get 77 on the final. Okay, so we can see that, you know, the final is outpacing their overall homework just slightly. Now, another question they can ask. Okay, a student needs to get a specific grade on their final. Okay, a student needs that 95 on the final. Okay, based on this equation, what original homework score would allow them to get that 95 on a final? Okay, so now notice we're putting the variable in for y. We're looking at that prediction outcome, and then we want to do our solving for x. So 95 minus 43.34, enter, and then divided by 0.460 equals, okay? So now this is a bad scenario here right now, right? So we know if a student wants to get a 95 based on their homework and based on this formula, they would have to get 112% in their homework grade. Okay, not possible in most schools. Okay, so that's what we have to understand is these prediction models are not perfect, and sometimes the solution you get might not be a reasonable answer with what we're looking at overall. Okay, now, a couple things to consider as we wrap up here. Extrapolation, okay, a very important piece. We should not use our least squares regression line for predicting values outside of the domain of x. Okay, so if we have our x values and they fall in a specific range, we should not use that to make a prediction outside. Okay, you know, a best example of that is on September 10th, 2001, okay, an investment in the airline industry was probably one of the best investments that you can make. All the models would tell you to invest in airlines, but the hard part is, you know, we all know what happened on September 11th, 2001, you know, and the airline industry basically went almost bankrupt across the board because of those events. So that's always the thing that we have to be careful of. If you predict outside of your domain of x values that were used to create the regression line, you don't know whether that pattern continues overall because we don't understand necessarily what events could affect, and those are confounding variables. They're outside of the scope of our situation to work off of. Okay, so now when you're looking at the in-class packet, if you want some extra examples to see worked examples of this in-class packet, pages 3 and 4 deal with creating least squares regression line and then using the least squares regression line to make predictions. Thank you and have a good day.